Welcome back. Today in this video we are going to see how to structure a B project. A B project is not made of a single specification and implementation containing the whole software, because all the complexity should be handled at the same time, leading to the inability to prove the software. Rather, the functional decomposition of the software is performed over several components, because the impossibility for one operation to call another one from the same component, the exception are the local operations that will be addressed later. In our example, M0 declares two operations, F1 and F2. In the implementation, it's not possible for F1 to call F2 and from F2 to call F1. So a B project contains a collection of models linked with the two main structuring mechanisms: imports, an abstract machine, and seize, an abstract machine. The modularity allows to manage software complexity by breaking down large software into smaller parts and to use the proof of the models with the smaller and simpler proof obligations. It's the principles of divide and conquer. An implementation imports other abstract machines in order to implement data and operations with the lower level machines. The imports clause may only appear in implementation. In our example, the implementation M0Y imports both N0 and P0. Operation F1 may call the operation F2 and F3 declared in these two components. F2 and F3 may also be used to initialize the variables in M0Y. The variables of an imported machine M have to be modified in the implementation by the operation of the calling machine M. In our example, F1 cannot modify the variable VV directly. Instead, the setVV operation has to be used. Variables are implemented in one and only one component. Hence, it's not possible to import machines declaring the same variables. The solution is either to create components with independent variable sets or to regroup the important components in a single one. In this example, the two machines N0 and P0 declare the same variable VV. It is not possible to import these two machines within the same implementation M0Y. In the second example, two components are created because F1 and F2 depend on VV and F3 depend on XX. Another possibility is to have one component N0 declaring both variables VV and XX and the operation F1, F2 and F3. Let's see how to split an algorithm containing too many instructions. For example, if we consider the operation OP, we may decide to lower the number of instructions per operation. The main idea here is to transform the operation OP into three operations, OP1, OP2 and OP3, that will be called in sequence. This is how the two modules look like when decomposed. Operation specification may look different in your case and depends on what you have to prove. This is another decomposition using two imported machines, N0 and P0. Imports may be applied iteratively to obtain the target decomposition. The decomposition graph has to be a tree, as it is not possible to import the same component more than once except for the top level component. To ensure that the properties proved locally, component PO still hold at global level. When a component sees an abstract machine M, the data of M may be accessed in read-only mode. In this example, the implementation S0Y is able to use a read-only getXX operation, returning the value of XX, as well as a constant CC. When a component sees an abstract machine M, the operations modifying M cannot be called. In this example, the implementation A0Y is not able to use setXX operation, as it modifies the variables of the seed machine R0. And we get the error message, illegal access to non-visible entity. The seize link is not transitive. In this example, T1 sees T0 and T2 sees T1. However, T2 does not see T0. When trying to use in T2 a constant defined in T0, we got an error message, undeclared identifier. A workaround consists in adding T0 as a seed machine in T2. We use seize on a stateless module, on a brother or cousin module, for read-only access to scene variables within substitutions, for a call to scenes operation that do not modify variables. Warning, scene variables are not visible in the invariant of the scene component. A stateless module contains no variable. It may contain sets or constants, either concrete or abstract. It may contain purely functional operations. It is imported at the highest level and can be seen from everywhere in the project. Two examples of such module issued from the C4B code generator. One component defining the various integer types, and the other defining the type and semantics of the arithmetic operators. The dependency graph is a graph made up of the project concrete modules and of the imports and syslinks between those modules. The dependency graph must not have any cycle. In this case, there is no valid order of initialization. In this example, a component is imported twice, red rectangle. A workaround consists in merging the two components that imported. In this example, a component scene, red rectangle, is not imported in the project. A workaround consists in importing the scene component in the top-level implementation. Local operations is a feature to ease the functional decomposition by avoiding too much levels of decomposition in the project. Local operations may be defined only in implementations, and local operations may be called from implementations operations, being global or local. Local operations are specified in the local operation clause. Their invariant is made up by the typing of the concrete variables, and they are implemented in the operation clause, like global operations. In our example, the operation op calls the local operation getMax defined in the same implementation A0y. You now know how to use the most useful clauses to structure a B project: imports, sys, and local operations. This is all for today. See you soon, and remember, formal is fun.